Okay, welcome to the fifth video that we're doing on derivatives. This one is the chain rule, and this is a topic that I've been hinting towards for a considerable while in previous videos. The reason why is that before I started prepping for this course, which I have taught a lot of times before, but I wanted to get some more feedback, and so I asked an old university professor just for some feedback as to what sort of things do I really need to focus on to prep students for first year calculus. And the chain rule was his number one thing. And interestingly enough, the other feedback I got from another source was students really struggle with composition of functions, which the chain rule actually happens to involve composition of functions. So I guess what I'm trying to say is this video, I want you guys to really focus on this one a lot, because this is a very, very major topic that you're going to need going forward for, not just for our course, but I assume most of you have post-secondary aspirations where you want to go into calculus. That's the point. That's why you'd take this course, right? So this is a pretty important section, and I agree with the professor I talked to. This is one of the really critical moments here. Is to, if you understand this concept, you'll do well, and if you don't really internalize and get the chain rule, you'll probably always struggle. So without any further delay, why don't we get started with just a little bit of a review, like I always do. We should talk about the verb differentiate. Differentiate means to find the derivative. And I'm doing this pretty much every lesson in this section here. It's important to know what a derivative is. If you were to have a graph which had one variable on this side, let's just call it y for right now, another variable on this axis right here, and you had a graph, and I don't know what the graph looks like. It could be maybe a reciprocal graph, or maybe it's not a reciprocal graph. Maybe it turns around and does all sorts of funky stuff, right? Well, the derivative is an equation for slope, and therefore you would then be able to find the slope at any given moment. If you wanted to find the slope right here, let's say along this axis, and you wanted to find the slope when x was 1, 2, 3, 4, 5, 6. If you wanted to find the slope when x is 6, a derivative is an equation that once you found that equation, if you plugged in 6, it would give you the slope. And obviously the slope here at 6 is very different than what the slope would be at 7. And it's also very different than what the slope would be over here at 8. And remember, that slope is really context dependent. This is where math really leads so well into the biological, the chemistry, the physical sciences, also into economics. There are a lot of different places where we can use calculus and the concept of derivatives. We're eventually going to lead into a concept of how when the derivative is equal to 0, how that sometimes is a useful thing, because that's a relative or local maximum or minimum. And sometimes maximum or minimums are useful. Like, for example, if this was plotting money versus time, you would want to know when the money is going to be at its maximum or at its minimum, right? Those are useful points to know. So anyways, I digress. Hopefully you have fully internalized what a derivative is, because we're going to take so many of them over the rest of the course. Really what's going to happen going forward is this unit here, we're going to talk about derivatives. The next unit, we're going to talk about other types of derivatives that aren't just polynomials. Then in the unit after that, we'll talk about how to apply them to word context problems. And then in the last unit, we're going to talk about integration, which is the opposite of derivation or derivatives. So really, this is what we do going forward from now on. All of what we've done in the pre-calculus and the limit section was building our skills to get to here. So, okay, so let's say this is our function. We want to find the equation that would give us slope for this function here, which you could write as, say, dy over dx. Or you could write as f prime x, or maybe you'd like to write it as d over dx for x squared minus 2 squared. Really, all of those mean the same thing. Right? Well, we've learned basically 3 rules so far. The first rule we've learned is the power rule. And the power rule works really in this case here. If you have a derivative of, say, x squared, it's 2x, because you pull the exponent down in front and then drop it down by 1. Now, that really only works if you have a single individual term. So then we learned rules for adding and subtracting, which was that if I give you the derivative of x squared plus x, this really can be the derivative of x squared, and you can also take the derivative of x, which is useful when you have multiple terms. However, that's not going to be useful here because these multiple terms are still inside a squared sign. Earlier today, in this lesson even, like less than 2 minutes ago probably, I talked about how one of the important things to know was how to do compositions of functions. And you could really consider there that there's really 2 functions. One of your functions is x of x squared, and the other function is x squared minus 2, and you're being asked to take the derivative of, now I gotta get this in the right order here, of f of g of x. That's really what you're being asked to do. You're being asked to find f of g of x prime, right? Where really the x squared minus 2 is inside the x squared function, which is why it's all of that squared. So that should be something you guys are familiar with. I'm trying to undo this here. Let's see, edit, undo, undo, undo. There you go. Don't want all that extra mess there. I do want that one because this does imply that we're taking the derivative. So hopefully you're familiar with this notation. You've learned it in 30-1. This just means take your g of x function and put it inside your f of x function. The analogy I'm going to use today is that there's something inside something else. There's literally a function inside another one. And this is actually really topical for me right now because my wife is pregnant. The analogy I use is that there is a baby inside of a pregnant mother. Essentially, the idea is that the f of x function is the mom, and inside the mom is a baby inside. And so you have one function living inside the other function. A lot of kids, they find this analogy very vivid because they'll recall it and they'll get the concept. So I'm going to refer to that as we learn the chain rule in the next little while here. So first I'd like to show you, though, that there is another way we could solve this. Even though there is a function inside another function, we could just expand this, right? I mean, this really is x squared minus 2 next to another x squared minus 2, which is going to give you x to the 4 minus 4x squared plus 4. Now I'm going to throw a derivative sign in front of this, implying that I still haven't actually taken the derivative of this yet. Now I could write the derivative sign in front of all three of these terms individually, but I think we're probably past that point now. I can now just go to 4x to the third minus 8x and just call her a day. And now I no longer need the derivative symbol because of the fact that I have taken my derivative. So, hey, that one wasn't so bad, right? I mean, if all I've got to do is square out the function inside another function, that wasn't too challenging. Except when I give you this. Well, now if I give you x squared minus 2, but it's to the power of 6, it would take you 5 minutes just to expand this. Now, even if you recall the binomial expansion theorem from the combination permutation unit from 30-1, which might save you a little bit of time, this still is going to take a while. And this is why the chain rule was then developed. Right? Now, hopefully, again, you can see that really what we have is a function inside another function. The baby inside is the x squared minus 2, and the larger function, the pregnant mom function, is an x, not x squared, that was the last one. We do this properly, Chris. It's the larger function is x to the 6. And really what we're being asked to do is g of f of x. We're being asked to take this function and put it inside that function there. So hopefully this analogy makes sense. X squared minus 2 is like the unborn baby that is inside the pregnant mom. I don't know. I think the analogy it helps kids to visualize, especially because students really do struggle with composition of functions. So hopefully you'll agree with me, though, that what I have written here so far, it's going to take a long time to expand out because of the fact that the mother function is to the power of 6. So there's actually a formula. So this is formula number 4 or 5, depends on what we're really up to. We've got one for the power rule, for add and subtract, for multiply and divide, and then this is the power rule for when you have composite functions. And so here is what's called the chain rule. Hopefully I said that. Yeah, this is the chain rule. So if the f of x and g of x functions, first of all, if you can derive them, if they're differentiable, and the function that you want to work with is a composite function, then here's the rule for how it works. You do f prime gx times g prime x. Essentially what you're doing here is you have to take the derivative of the mom with the baby inside. That's how I like to use this terminology here. F is the mother function, g is the baby inside function. And so what you do is you take the derivative of the mom function, but you leave the baby inside, meaning that whatever you have inside, that still remains your variables inside there. But then afterwards, you have to chain on, which is the reason why they call this the chain rule, you have to chain on an extra derivative which is the derivative of the baby inside. So, wow, that just makes no sense. I mean, when people listen to me talking about this, they walk by a math classroom and they go, okay, I'll take the derivative of the baby. And you're like, what are you talking about? So let me show you how this will look, though, because this actually isn't as hard as you think it is. The way this works is if you want to take the derivative of x squared minus 2 to the 6, it looks like this. You take the derivative of the main function. Well, the main function is really x to the 6, right? It's something to the 6. So you bring 6 down in front, and you drop it to the 5, right? That's how you would derive this 6 right here. You drop the 6 in front, drop it to the 5. However, the baby inside will then stay inside, which will give you x squared minus 2. That inside part remains. Then the chain rule occurs where then when you take the derivative, you have to chain on the derivative of the baby, which is one of the reasons why I like Leibniz notation so much, is that this now lets me know that I still have to take one more derivative. Whatever was inside the original function, the inside composite part, well, I have to derive that too. So I can still write this first section again right here. It doesn't change. But then the derivative of this last little bit is 2x. So I would be content if you stopped there, but some people would actually maybe write it like this, 12x and then x squared minus 2 to the 5. And that would be your derivative. Right, I just took the 2 and times it by the 6 in front. So now I showed you an example, and I mean, hopefully you're able to follow a little bit of what I was doing. But I mean, I would totally understand if you were looking at me very strangely going, what did you do and why? So I'd like to show you over the next couple of slides a little more details as to exactly why this works and why this was allowed to happen, because it is actually fairly simple, but you have to wrap your head around what goes where. So here's one more time. This is the official kind of notation. And boy, especially if you're in my class, if you've learned anything in the last year in math, from 30-1 to calculus, it's that notation is so important because we need a shorthand way of describing what we're doing. And so little things like the little prime symbols and the brackets and these D's and the F bracket, G bracket, X, all of that is a symbol that means whatever the action is that you're going to do, right? So here's the symbology. If you want to take the derivative of a function that has another function inside of it, the mom with the baby, take the derivative of, see the prime right there, take the derivative of the mom, but leave baby inside, then chain on by multiplying the derivative of the baby. So let me show you how that would look a little differently in using Leibniz notation. That's why I like the dy over dx notation. If I wanted to ask you to deal with this, sometimes it works well if you use like a bridge, like if you use a u as like an intermediary function. Let me show you how this would look. We had the function, which was, what was it? X squared minus, I forgot already, x squared minus 2 to the 6, right? That was our function. So what I could do is I could say, well, why don't we let x squared minus 2, why don't we let that be equal to u? So I'm just going to change out a variable, which means that when I want to take the derivative of y with respect to x, which really means I want the derivative of x squared minus 2 to the 6 with x's in it, this makes sense, right? I want the derivative of this thing right here, but I want there to be x's in it. Well, now I have a little bit of an issue, because if I substitute in x squared minus 2 for my u, I can now take the derivative of u to the 6, right? Because really, this is now u. Well, here's the problem. This dx on the bottom here is a notation which lets me know that I'm deriving with x as my variable. And using substitution, I've now changed it so that, well, that's not really what happened. Now u is my variable. So if you can see what happened right here, what you could do is you could take the derivative of y with respect to u, and then after that, you can take the derivative of du with respect to dx, and hopefully you can kind of visualize those would kind of cancel. So why not continue this right here? Really what I'm doing then is I'm not going to take the derivative of u with respect to x. I'm going to take the derivative, like I'm going to do du over dy over du, right? Because really, this is y still. This was y right here. I did a little substitution. And then what I'm going to have to do is I'm going to times by the derivative of du over dx, which means that when I'm done, I'm going to take the derivative of du 6 over du, which, by the way, don't forget, that really was y, right? U to the 6 is really what y is. That's my original function. And then I'm going to take the derivative of u. Well, I'm going to substitute this in here. Didn't I say a second ago that u was going to be x squared minus 2 over dx? Which means that when I derive this guy right here, it becomes 6u to the 5, right? And I mean, I can do this, right? Now that I've changed y out for u to the 6, right? Because really, think this through. Y was x squared minus 2 to the power of 6, but I've changed the x squared minus 2 to be u, so that now y is really equal to u to the 6. So I changed out my dy. Where was it here? I changed out my dy for u to the 6, but I derived it with respect to u, because u is now my variable. It gives me 6u to the 5. But then the problem is that that doesn't really work, right? I really need for like those du's to cancel right there. Let's cancel those again, though, because I don't actually want those sitting there. And then I have to chain on the derivative. Well, this is now the derivative of the baby inside. And x squared minus 2 over dx, I can derive that because the variables match up, so this gives you 2x. And then in your last step, I have two different variables. I have u's and I have x's. So I replace the u with x squared minus 2, which is what I had always said it was. And that's kind of where this comes from. Right? So that's how the chain rule works, is that you really want to do dy over dx, but you can't. You have to use a bridge in between. So you do dy over du, and then you do du over dx, and then those derivatives cancel. Right? I mean, these notations cancel, leaving you with y over x like you wanted in the first place. So, okay, you may want to rewatch that because, like, this is one of the most impactful things that we're doing. If you can wrap your head around this and follow what we're doing, you're going to do fine going forward. This is really the part where I remember when I was in university, this is where a lot of kids start dropping out. And this explains why there's a 50% failure or dropout rate to calculus, because it's hard. It's confusing. This all of a sudden comes out of left field. So I really hope that I do a good job of explaining this to you now, and that we can build a nice, safe work environment for you to build these skills. The advice I'd like to give you is don't just do my assignment. You're going to need to do some more practice just for your own well-being, especially because you have a midterm coming up. You don't want to just do my assignment questions because really there's only just like a little taste of everything. You're going to want some good, solid practice on this. Now, I should point out one more thing. The reason we call this the chain rule is that this can work for multiple functions that have composites inside. Like you can have a function inside another function inside another function. Like you could have f of g of h of k of x, right? You'd write that as f, g, h, k, x. Right? Or you can have a k inside an h, and h inside a g, and g inside an f. Right? Using my analogy of like a baby inside a pregnant mother, it doesn't really make a lot of sense because then you really have a baby inside a baby inside a baby inside a baby. So, or a baby inside a baby inside a baby inside a mom, maybe. So I like a different analogy. I like talking about the Russian nesting dolls. If you know what I'm talking about, those little dolls where you have one big one and there's a slightly smaller one inside and a slightly smaller one inside. Think of that when you think of the chain rule, because basically the idea is you always have to chain on a derivative of the thing that was inside on your next step. So we should do some examples. Let's try this one here. I'm going to try this one the long way first. And go through like the really nitty-gritty details of why this works. And then slowly but surely we'll speed it up a little bit. So here, we want to take this guy's derivative. And hopefully you'll notice that there is a function inside another function. What you have is a 2x squared plus 3 as a baby inside of a larger square root function. Right? So based on that, we need to, I like to write it like this. We're going to let u, the baby inside, be equal to 2x squared plus 3. Now, we would like to find dy over dx, but we can't do that in one step. So what we're going to do is we're going to find dy over du, and we're going to times that by du over dx. It'll get us to the same spot when we cancel those. So dy over du, well, y was supposed to be equal to 2x squared plus 3, but I just let the 2x squared plus 3 equal u, So really, I'm taking the derivative of the square root of u, and I've replaced that baby inside with the letter u. That's the first part. Then the chain rule part says then you have to take the derivative of u with respect to x. Well, I mean, I could write du right here again, but that's what I wrote above. Why don't I replace this u right here with 2x plus 3? Or 2x squared plus 3. Now, this now makes a lot more sense because now we're taking a derivative of something that has u as a variable, and this notation down here indicates that, yeah, you are taking the derivative of that with a variable, right? U is your variable. There we go. X is your variable here. There you go. So when I derive this, the derivative of u is 1/2 u to the minus 1/2. And then we chain on the derivative of the baby, which is 4x. Now, at this point here, we are done with our derivative symbols, but I do have to do one more thing. I have to resubstitute what u is, because what we really wanted was dy over dx. So it sure would be nice to have x's as my variables again, right? So u was 2x squared plus 3. There we go. There's my derivative. Now, I'd be content if you guys left it there, but a lot of people would expect that you'd cancel this 2 and this 4. And maybe you'd simplify it a little bit and you'd make it 2x squared plus 3 to the minus 1/2. They'd expect this 2 and this 4 should cancel. And they probably would write them in some sort of order where like the single monomial type term would go to the front rather than at the back. So there is our derivative. Now, once you get the hang of this, you don't need to go through the whole process of doing dy over du every single time. So I'm going to erase this, and if you want to, I mean, just rewatch that little snippet of video there again, right? Which you should do. You really should. Like right now, seriously, stop, rewatch that. It's worth your time. Okay, you watch that again, right? As I laugh you. Hopefully you did. But here, let me show you how to do this a little bit faster. Once you get the idea how this derivative works, the formula was take the derivative of the mom with the baby inside and then times by the derivative of the baby. So really, when you want to take this derivative here, you're asked to find the derivative of 2x squared plus 3. So here's another way of writing it here. I'm going to make this 1/2 2x squared plus 3 to the minus 1/2. Right? What I did is I just recognized that the 2x plus 3 is really the baby inside, and that the main core outside of the composite function is the x to the 1/2. So I brought the 1/2 down in front, made it drop to the minus 1/2, but I left the baby inside, and then I'm now going to times by the derivative of the baby. Which means that I don't have to rewrite this first section because it's done with its derivatives. If anything, I can use this time to rearrange it algebraically if I need to. And then now I'll take the derivative of this step over here, which is your 4x. And there we go. I got the derivative in a much faster way. Now, I always recommend rewrite this derivative notation. Do it step by step by step. Don't try doing so much of it in your head. I find a lot of students, they have a little bit of an ego. And I mean, I don't know almost any of you guys right now, so I hope this doesn't come off as insulting. But please don't let your ego get in the way where you go, oh, I'm smart. I can do this all in one step. I got this. You know, don't worry. I got this. I won't make a mistake because you probably will. This is a pretty basic level problem here. We're going to be working with derivatives inside derivatives that have chain rules and product rules and quotient rules. And even though you might have been able to just look at this and say, well, okay, I dropped the 1/2 down in front. I made it a minus 1/2 right here. And then you go, well, I need to derive the baby inside. Oh, I'll just call that 4x. That don't get me wrong, that can work. But my goal is to help you build healthy, strong habits for when you get to university. And I would recommend every time you do a chain rule, rewrite the derivative of the baby on the outside, just to do it like step by step. Don't make a simple mistake. That's the advice. You can either choose to take it or not, I guess. So let's try another example. Let's take this guy's derivative. Now, at its core, there is a function inside another function. The function inside, the baby inside, is the 1 minus x to the 4. So if we want to use this notation again, I could let the u be equal to 1 minus x to the 4, which really means that y is equal to u to the minus 1/3. Right? Because don't forget, a third root is a 1/3 exponent. But if it's on the bottom of a fraction, it is a negative 1/3 exponent. So if I want to find dy over dx, I can't do it directly. I'm going to do du. Oh, no, that's not right. Too far. I'm going to do dy over du. I'm going to take a derivative of y with u's in its equation. And then I'm going to take a derivative of u with x in this equation. And you can even see the way I wrote it out here. Here's an equation that has y with u's in it. And here's an equation that has u's with x's in it. Right? Those essentially cancel in terms of the way our terminology works, and you'll be left with dy over dx. So we need the derivative of u to the minus 1/3 with respect to u. And then we need the derivative of 1 minus x to the 4 with respect to x. Good news for both. The variable which we want to work with, we are deriving with respect to. That's not always the case. It won't be in our next lesson on implicit differentiation, but it is right now. So, okay, so let's derive this one here. Power rule says drop the 1/3 down in front, and then drop the exponent by 1. I did that. Hopefully I don't need to talk you through too much about how I got the negative 4 over 3, right? Because negative 1/3 minus 1 more is negative 4/3. And then when I derive this one, 1 derives to nothing because it has no slope. And then it'll be a negative 4x to the 3. To try to finish this off, I'm going to do a couple of things at once, right? In this sort of way of doing it, I could do negative 1 over 3. Then u, I should replace it with 1 minus x to the 4. Make that go to the minus 4 over 3. And then last step here, let's clean it up a bit. You have two negatives so they can cancel. Why don't I bring the 4 and the 3 to the front, and let's put our monomial at the beginning, and then let's put our binomial with the negative exponent after it, and there's our derivative. So if you need to rewatch that, I'm now going to show you a little bit of a faster way. I still want to make sure that you do a good job of notating this and indicating what's happening, but all of that u, y, u, x stuff where you use y as a bridge, it's really unnecessary once you get the hang of it. So here's the chain rule a little bit faster. I'm going to go y equals, I'm just going to make one quick change. I'm going to make it 1 minus x to the 4, and I'm going to make it go to the negative 1/3 just first, just so that it all looks kind of nice. So here's how the chain rule works. If I want to take the derivative of y with respect to x, it's the derivative of 1 minus x to the 4 minus that with respect to x, which is minus 1/3. Keep the baby inside. Do not remove the baby and change the baby back to x. The in the brackets function stays the same. Drop the exponent like I did the other time, but then you still need to take the derivative of your baby. Now, I always recommend do this in stages so that you can see that, look, this section right here, I don't need to do anything more to, but I still have one more derivative to take. I have to take the derivative of the baby. I like doing this in stages just because I know it's going to get more complex. And there's our derivative. If you want to clean it up and bring the monomials back to the front, that's fine. That makes sense. So we have done a couple of examples, both using the substitution method of du over dx, but I'm just going to stick with the chain rule from now on. So I'm going to go a little faster. I'm going to blur through this one a little bit quicker. And hopefully here I'll show you why I want your notation to be so thorough, because the baby inside today is a quotient rule. That's the new little twist here, is that when I want to derive the baby inside, it actually requires a fairly complex rule on its own. So here's how this would look. I'm going to differentiate with respect to x. So that's going to be d of 2x minus 1 over x plus 2 to the power of 6 with respect to x. I can do that. X is my variable. So I'm going to go 6, 2x minus 1 over x plus 2 to the 5. Right? Drop the exponent down in front. Keep the baby inside. Drop the exponent down 1. And then now we're going to derive the baby inside. And this is the biggest reason why I'm going to suggest don't do multiple steps in your head. Because this guy right here in its own right is a quotient rule, which we learned last lesson. So this is why I love Leibniz notation. Now I can just keep writing this first little bit here. I've got to keep writing it every single step. But now I can apply the quotient rule. And the quotient rule is the derivative of the, let's see, what is it? It's the derivative of the top. I got to remember what the quotient rule is. I don't want to screw this up in my notes here. Let's go back. Quotient rule is bottom derivative top minus top derivative bottom. Oh, I already forgot what it was. I just looked at it. Bottom derivative top. All right. So it is the bottom. Okay, it is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And all of that is the derivative of the baby. So the reason why I want to point out an example like this is that I don't think you can derive that little piece in your head. Sure, if you were deriving just 2x and make it 2, sure, that's easy to do. But when it gets more complicated, when the composite functions inside and outside get more complicated, you're going to want to make sure that your notation is crystal clear. So how many derivatives do you have to take? 2. There's 2 remaining derivatives. So I'm getting kind of a head start just by rewriting the part that does not require another derivative. And this one here does not require another derivative. This one over here does not require another derivative. And this guy down here does not require another derivative. Whew. Okay, so then let's talk about the stuff that does have a derivative. 2x minus 1, it derives to the number 2. And x plus 2 derives to 1. So there. Now we're done. Now, a lot of times this would be sufficient. I'm actually going to accept it at this point here, but it wouldn't hurt just to remind you that you can sometimes do a little bit more cleaning up and make it look just a little bit nicer when you're done. For example, I could take the numerator right here and turn it into 2x plus 4 minus 2x plus 1, which means those 2x's cancel, which really means that you have 5 in the numerator over x plus 2 squared. And it's really being times by this guy, which I'm just going to draw an arrow to indicate that he's just kind of coming down. Check my math there again. 2 times 2, 2x. 2 times 2 is 4. Distribute the negative. Negative 2x plus 1 because you're timesing by 1. Negative 2x cancels. 4 and 1 is 5. I could take this 6 and this 5 and combine it to give it 30. And then I could say that I have 2x minus 1 5 times. And then I could actually say that I have x plus 2 7 times. Right? Because there's 5 from this guy here, plus there's 2 more there. So if you were doing textbook questions, they probably would have answered it like this. I would have been content if you just probably stopped right about there. Because you have your derivative, we're good to go. And often I'll say, do not simplify. But if it asks you to simplify, this would probably be the best way of doing that. So, okay, hopefully that made sense. Rewatch if you need to. Ask me questions. Most of you do not ask me enough questions about the notes. Many of you ask me questions about the assignments, but not about the notes. And maybe I'm doing a fantastic job in these videos, which should be awesome, and I'm very happy to hear that if that's the case. But if you're not understanding my lessons, which they're getting tougher, make sure you make a list of questions to ask me about how to do these concepts. Okay, here's where this gets taken up another notch. What we have going on here is 2 different chain rules with a product rule in between them. Because you have a baby inside the x to the 3, the baby being the x squared plus 1. And you have another baby inside the x to the 4, with the baby being 2x minus 3x. So apparently there's a couple of moms who both have babies and they're going out for a walk. And we have to multiply them by each other. Okay, this analogy got kind of dumb there. Anyways, point being here, we need to make sure we are crystal clear on what's occurring. the first thing that's occurring is we have a product rule. So to find the derivative of y with respect to x, the formula for the product rule is the first portion times by the derivative of the second portion plus the second portion times by the derivative of the first portion. So then the question is, well, how many derivatives do you have to take? We have to take 2 derivatives. However, this derivative here I'm going to put in red, and this derivative here I have to put in purple. Each of those is actually a chain rule. So let me write this out in some colors. This is going to be equal to x squared plus 1 to the 3. That ain't changing. And 2x, oh, not 2x. I'll just get rid of the whole thing and try again. And this 2 minus 3x to the 4, it doesn't need anything extra. But this one in red here is a chain rule, so there is a baby inside. So I'm going to bring the 4 down in front, keep the baby inside, and then I'm going to take the derivative of that baby in a subsequent step. And then over here, I might soon be running out of room here, I'm going to take the derivative of the function with the baby inside, and then I still have to take the derivative of that baby. So looking back here, right here, I had to take a derivative. Right here, I had to take a derivative. You might think, yay, I'm done. I took my 2 derivatives. But because they were chain rules, I still actually have an extra baby derivative to take in 2 different locations. So here's our final answer. And I mean, this is starting to get to be a lot of room. I'm going to recommend you guys need to make sure you get in the habit of saving a lot of room for your questions. My assignments are usually, like when I make the answer key, they are usually like multiple pages long. So if I see you trying to cram all this into one little spot here, I mean, if you can do it neat and organized, sure, but most people can't. Make sure you save yourself a lot of room. I mean, all I'm doing so far is just rewriting the first stuff that I didn't have to derive. Really, all I had to derive was this guy and this guy. That one's 2x, and this one's -3. So last step, let's clean it up a little bit here. Let's make it a -12, and then we've got an x squared plus 1 to the 3, and a 2 minus 3x to the 3. And then on this one here, to clean it up, let's put all our monomial terms first. So let's put 6x in front, and then we'll do 2 minus 3x to the 4, and x squared plus 1 squared. Now, I actually would have been content if you just left it there, like this step right here. When I give you an assignment or I give you a test, that is, in my opinion, that is done. We have a derivative. All the derivative signs have been taken. I mean, this is an ugly equation. Even you got to remind myself, what's this equation for? Well, this is an equation that'll find you the slope. If you want the slope at any given point, just plug in x and it'll give you the slope. All right, but the next one's kind of nice because it's a little bit more simplified. We can actually factor now as well. In these terms here, there's actually an x squared plus 1 twice in both of them. And, oh, I put a bracket in the wrong spot. Look at this. Good thing I went over that. That bracket is in the wrong location. That is such a common mistake where you just miss a little thing here. The reason why this is important is that there's an x squared plus 1 squared in both of them. And there is at least a 2 minus 3x to the 3 in both of them. So if you factor that out, what you'd be left with is a 6x minus 12, just because I'm going to put that in a different order there. And then you're also going to be left with a, let's see. Well, actually, no, I don't want to write it like that just yet. Let's not do that. You're going to be left with a minus 12. And then here, let's see, you pulled all of those ones out, and all of them but 1. So then there should be an x squared plus 1 left there. And then I need to add to this guy right here all of the, let's see, the 6x I didn't pull out. And then all of these ones but one came. And then both of those ones came. There's another way of writing it. I wrote it in a factored format. I mean, I don't see that either of them has much value, because what's the point of a derivative? Well, it's an equation for slope. Well, I don't know whether this equation or this equation or this equation, whether really any of them are better, because either way, you got to plug in x like 6 times. So, okay, I've got one last example that I'm going to do with you guys, and then I've actually got a slide of examples that are just meant for your own practice later. And then that's it for the topic. So let's do this last one. This is an example of a baby inside a baby, or those Russian nesting dolls where one is inside the other. What we really have at its core is there is an x squared plus 1 as the inside baby. And it is inside a function that is a 1/2 function. That then gets combined with this x to then be inside another function that is a 1/2 function. So you actually have like multiple functions inside of each other. So it doesn't hurt to be really careful with your notation. So let's give this a try. If I'm going to find this derivative here, it's going to be equal to the derivative of x plus x squared plus 1 to the 1/2, and all of that is to the 1/2. So I used my first step to change all of my square roots to 1/2s. So hopefully that made sense, right? I changed the inside square root to 1/2. I changed the big square root to the 1/2. I haven't actually taken a derivative yet. So now I'll take a derivative. If I take the derivative of this big function here, the big mama function, right, the outside nesting doll, is a 1/2 and then minus 1/2. But the baby has to stay inside. And so our baby in this example is x plus x squared plus 1 to the 1/2. That baby still remains. But I have to take the derivative of the baby, which is x plus x squared plus 1 to the 1/2. I still have to take the derivative of what's left inside. Oh boy, this is where sometimes you need a lot of room. I just said that on the previous slide. So I am rewriting the 1/2, the x plus the x squared plus 1 to the 1/2, all to the minus 1/2. And every step, I'm going to have to rewrite that, by the way. It's going to stink. Okay, now I have to take the derivative of this guy. Well, this really means take the derivative of two different things individually. I have to take the derivative of x, which is 1. And I also have to take the derivative of this guy over here, which is going to be 1/2 of the baby inside to the minus 1/2. And then I still have to derive the extra baby inside. And now, as you're following along, this is where kids' heads sometimes start to spin, where you're like, oh my goodness, there are brackets everywhere. And you need to make sure you're crystal clear about where they go, because I put a large square bracket around all of this, kind of in the vein that all of this stuff right here needed to get derived. So I couldn't just leave it as this times 1, because really what ends up happening is this whole term here is times by a binomial, right? This is really a binomial. There's term A here and there's term B here. Its derivative then is term A here and B here. And so I need to make sure that I'm very careful on those brackets, because if I'm not and I don't write them there, you might be tempted to think that all of this stuff right here is just being times by 1, and therefore you don't even need to write this 1 anymore. You'll be like, ah, it's redundant. But it's not the case. All right, back to where I was. I got to rewrite everything that does not have a derivative sign in front of it. So you can see why like assignments are sometimes like 10 pages long. They should be. If they aren't at this point here, I mean, don't get me wrong. It is possible for you to condense things, but do not take shortcuts. You'd be shortchanging yourself on the whole point of this. So, okay, we are now done, and I am very much content to be done at this step here, because even though I could do some work, like for example, all of this stuff right here, I could factor it into that binomial there. I don't want to. That does not look fun, and I don't see much point to it. So I do need you to be aware that a university professor may ask you to do some simplifying. If you look in a workbook or a textbook, they may do some simplifying. but I don't see much point in distributing this guy into there. At best, I could see that you could cancel this 1/2 and that 2 there. You could do that. I don't see much point in that. But otherwise, you'd have to distribute this whole term here and times it by 1, and you'd have to times it by this term over here, which is really x times x squared plus 1 all to the minus 1/2. I don't see how that's helpful. So let's stop here. This is our derivative. Remember, a derivative is an equation for slope at a point. If you give me a point, I can tell you the slope. So here's your derivative. You can see why, I mean, if I just, when I teach my classes normally in school, and I leave some calculus up on the board, and other students start looking at it, it really is a foreign language. They look at it and they go, I have no freaking clue how you went from step 1 to step 2. Like, this is some challenging stuff. So, like I always nag you, ask me some questions. Okay, I've been saying all along, you guys need practice. Like, this section here is a little less about you seeing the aha moment tricks. And this particular section here is more about just building some skills, because that's more what this is about. The first 2 sections was more algebra type skills, which were really based on algebra that you learned in grades like, say, 9 through 12. I mean, you still need algebra in this section here, but it's changed a little bit. You need to now know your new rules, which is the power rule, the adding, subtracting derivative rules, the multiplying, dividing derivative rules, and the chain rule. So I just counted 6 grand total there. The 4 main operations, the chain rule for compositive functions, and the power rule, which is kind of our starting leading one. So you need to know how to do these 6 things. So anyways, here's some practice. I'm not going to do these. The point of this is not for me to do them now, but for you to get some practice. And I strongly recommend after you do that, find some textbook questions and practice. Don't just do the assignment, because we have 3 weeks. And in this 3 weeks, yes, the thing that's due for marks is your assignment. And you could just do that and do very well on it. But you have a midterm coming up in a week. And once we finish this week here, when you want to write your midterm, you're going to want to spend some time getting your reps in, just like doing scales as a musician or practicing, dribbling or free throws as a basketball player, or being in the garage shooting hockey pucks at a washing machine like Sidney Crosby did as a kid. You got to get your reps in. You got to practice, right? So please do your practice. If you need questions, I will help find you some. Okay, anyways, I feel like I've said that for the last couple lessons. We are almost done, guys. There is one more lesson after this, and then that will be the end for this section. And then the week after that, then after this assignment is due, after this week of 3, whatever point you're watching this, you had 3 weeks to work on it. I hope you're not watching this on week 3. That's not going to be good news for you if it is. But the week after that, you got a midterm, and that midterm is worth 30% of your grade. So we got some work to do to prep for it, right? So, okay, I'll stop the video. Please get a hold of me, like I always say. Email me, ask me questions. Advocate for yourselves. Get some help, okay? So we'll talk to you later.